Hello everyone, my name is António Ramires. I'm a PhD student at the Music Technology group of Universidade Pompeu Fabra. Today I'll be presenting you the TIV.lib, an open source library for the tonal description of musical audio. This work is conducted by me, together with Gilberto Bernardes from Inesctec and University of Porto, Matthew Davies from CISUC from the University of Coimbra, and Xavier Serra also from the Music Technology group of Universidade Pompeu Fabra. I'll start by describing tonality, which can be a system of relationships between a series of pitches forming melodies and harmonies, which have a tonic or central pitch class as its most important or stable element. Automatically characterizing the tonality of audio enables several applications like audio fingerprinting, music recommendation, retrieval of audio in large databases, harmonic mixing, chord recognition, structural segmentation, or even beat tracking. Normally, approaches for tonality description use chroma vectors as the representation. This divides the energy of the spectrum of an audio in the 12 tones of the Western chromatic scale, and at the end we get a 12-element vector where each element corresponds to the energy of each pitch class. On the right we see an image by Maynard Muller where we can see an example of a series of chromas in the bottom of the picture, which are synthesized from a C major scale. Several algorithms have been proposed to create this representation. One of these, the earliest one, is the pitch class profiles by Fujishima. A very common pitch class used is the harmonic pitch class profiles by Emilia Gomez. There's also the CRP and the NNLS chroma. And finally, the tonal interval vectors, which are not a chroma representation, but I will describe these on the next slide. The tonal interval vectors are inspired by geometrical models of tonal pitch, for example the ones proposed by Krumhansel, Lerdahl, Schuh, Hart, and they represent the n-node pitch configurations on a 12-dimensional space by a unique point, which is named the tonal interval vector. Besides having information about the pitch class, it also considers information about the intervallic nature of the audio. To calculate it, we take a chroma vector, we apply a discrete Fourier transform to it, and we apply some pre-calculated weights and the L1 norm, and finally we have the TIV. To unify the implementation of the tonal interval space and its features, we develop the TIV.lib. This allows to calculate the TIVs from any chroma representation. It's an open source implementation and both in pure data and Python, and can be accessed at my GitHub, which you can go through this link. We only have very common dependencies such as NumPy, and it's very easy to integrate the TIV.lib with common MIR libraries such as Essentia or librosa, and you can see some examples of these inside the GitHub. From this tonal interval space, we can extract several features, and in this slide I present some of them. From the magnitude of the different components of the TIV, we can extract features related to the scale of a music piece, such as the diatonicity, chromaticity, or whole toneness. From this vector, we can also extract measures of dissonance, of harmonic change throughout a music piece, the key of an audio recording, and the Euclidean and the cosine distance between two tonalities of pieces of music. I will now detail a bit these features, starting with the TIV magnitudes, which, as I said before, represent the intervallic content of the TIV. It can be easily seen that a large magnitude in one of the coefficients of the tonal interval vector indicates how evenly the pitch profile can be divided by n over k, where n is the number of pitches in the pitch class profile and k is the component of the vector. Therefore, the first component corresponds to the chromaticity, the second to the diadicity, the third to the triadicity, the fourth has a meaning of a diminished quality, the fifth of diatonicity, and finally the sixth of whole toneness. One of the characteristics of the TIV mag is that it is invariant to transposition or inversion, and therefore all major triads or harmonic minor scales share the same Fourier magnitude and therefore the same TIV. As the magnitudes are invariant to transposition, we can use the phases to indicate the transposition which is under analysis. The function TIV combine, instead of forcing you to combine two audios and then calculate their TIV, it allows to do this process directly on the tonal interval vectors. There are then two distance metrics, the cosine distance, which is an indicator of how well two audios fit or mix together, and the TIV Euclidean distance, which is a very similar metric to the tone edge distance. Finally, we have the harmonic change, which outputs the harmonic change detection function, where we can see how much a track changes harmonically through time. To show the usefulness of the TIV.lib in a clear use case, I'm gonna present you now an example of it. I will now play a short example of how the features that are calculated from the TIV relate to musical concepts. For this, I will play you Kraftwerk Space Lab, and this track starts in the whole tone scale and then moves to a diatonic one. In the background, you'll see the HPCP representation of the audio and three features: the chromaticity in white, the whole toneness in purple, and the diatonicity in orange. If you want to play around with the TIV.lib and its features, we've created an example Jupyter notebook, which is hosted on Google Colab, and where we showcase several use cases for this library and how to run it and how to use it. It can be accessed at the link you see on your left. To sum up, I've presented you the TIV.lib. We have a Python and a pure data implementation, and it can be used both in online and offline scenarios, and it's open source. So we are open to pull requests, and I will be really happy if you experiment with it a bit and give us your feedback. For future work, we want to investigate further on the pre-processing stages, which chroma representations work best for each situation, and we want to investigate its application on navigating large databases of sound, and we want to implement these on one of the most common MIR libraries, such as Librosa or Essentia. That's it for today. Thank you very much for your attention, and I'm looking forward to your questions.